This talk is titled Challenges and Opportunities for Probe-Based Information Technology. This is a talk that was given at the APS March Meeting on March 24, 2011 in Dallas, Texas. So I want to begin with a discussion of some of the challenges facing information technologies that are based on silicon. And this is a graph that is constantly being updated at the ITRS, the International Technology Roadmap for Semiconductors, every year. And it's basically a diagram that's illustrating Moore's Law. So the vertical axis, which is traditionally points downward, is basically the Moore axis. So making things smaller and smaller. The feature sizes have been steadily decreasing, but below maybe 15 nanometers or so, it's not clear what is going to happen. There's a big cloud here. And at the same time, there has been a push to try to broaden what it is that silicon-based devices can actually accomplish, and to broaden what it is that silicon-based devices can accomplish. And this type of diversification is also known as the more than Moore axis, and basically it would involve integration of analog capabilities, maybe passive devices, sensors, and so forth. Of course, you really like to be over here where you have very small devices, inexpensive, that are doing lots of different things. So the question that I want to pose is whether scanning probe microscopy technology is also subject to Moore's Law. So if we take an AFM, the question is, can we scale it down to smaller and smaller sizes and increase the functionality and the capability, and perhaps have some direct rather than indirect impact on information technology? So is it possible to use the tips of atomic force microscope probes to write and read bits, for example, to make logic gates, or to do other things related to sensing? So this may seem like a very outrageous or sci-fi based prospect, but in fact the idea of using thousands of cantilevers was in fact envisioned and was given the name the Millipede Project. This was basically Gerard Binig at IBM, who was the co-inventor of the atomic force microscope, quickly with the others realized that there was a potential for using probes for writing and reading bits of information on scales that were much smaller than the current technologies. But of course there are many challenges, and one of them is simply to scale the functionality of atomic force microscope, which is a complex instrument, into a very small size, and keeping it, of course, the price low as well. So the idea of fitting 1,000 AFMs into an iPod, this is actually envisioned well before we even knew what an iPod was, so maybe we should have said Walkman. But the other question is, what is the medium? So what is it that is being used to store information? And finally, there's sort of a business end of this, which is, can you outrace, can you outlast competing storage technologies? So I'll refer you to some of the websites that discuss some of these issues in more detail. Basically, the design of a system that would allow 1,000 AFMs to work in parallel is conceptually straightforward, even though it may be very challenging to implement. Basically, you have a sled which would hold on the order of 10 to the 3 AFMs. You need to have some way of measuring their deflection, all in parallel, and then basically you have a common sample sled that would move in the X and the Y directions. It would be MEMS based. And so the amazing thing is, in fact, that all of the things that I would have naively thought to be very challenging were in fact were developed and were quite successful. So this is some pictures taken from the IBM Zurich laboratory, where they demonstrated actually 4,096 of these probes acting in parallel. So basically you have a MEMS scanner which can scan about 100 microns or so, and then there are electromagnetic coils which are then used to actuate the scanner. There are methods that were worked out for optical detection of the deflection of the individual cantilevers themselves, and arrays of these cantilevers were also developed and integrated with very sharp probes that were shown to last sufficiently large amount of time. But the real question is, what is the medium? So the one that was actually envisioned by the IBM group was to use the thermomechanical writing of a polymer film. There are actually sort of three main threads that have been pursued, and in fact this was a consortium of companies that were basically working on similar ideas but perhaps slightly different implementations. So this was the one that was pioneered by IBM, but there were also phase change media, where you have basically electrical detection of the nanocrystallinity of a material, and these companies were working on that. And then you had the ferroelectric memories that were using the spontaneous polarization of a material that could be reoriented with electric fields and detected also through electrical methods. Now this is actually a slide that I borrowed from another PowerPoint or PDF presentation as I was researching this talk, and so I will try to. You can find the full talks basically with the references down here. I do want to point out that as I was looking, I was trying to decide whether it was really appropriate to borrow from other people's slides, but then I saw that it was actually a very nice presentation from ST Microelectronics, and in their slide they had another slide from Seagate, so I thought I was encouraged by that. So that was another example of a slide quoting another slide. But then I looked more carefully at the slide, and I saw that actually this diagram was my diagram. So this is the actual diagram that I have made, and you can see that it was repurposed. Actually, pretty sure I know the person who took this, and of course I have no problems with that. I had a long-standing collaboration with Seagate when they had research facilities in Pittsburgh. But basically the idea of having a spontaneous polarization was one of the main threads as far as media for storing information. Well, what happened to the millipede? So why this was envisioned maybe a decade ago, and what happened was flash. So flash, of course, everybody's familiar with it. It's a ubiquitous technology. We all have our pen drives, and so the idea of competing technologies is something that you always have to contend with. So not only was flash memory a very inexpensive technology, but it certainly was very cute as well. I'm going to do this again. So flash memory is something that everybody essentially knows about. It's a ubiquitous technology. Everybody has a pen drive. Everybody probably has some micro SD memory, tiny little things in their phones. Flash memory is not only extremely inexpensive right now, but it's also terribly cute. And this is very difficult for a millipede, which is not the most lovely object, to actually compete with all these cute implementations of flash memory. Well, basically what is happening with millipede is that right now it currently is residing at the bottom of the valley of death, which is the curve, basically a universal curve for all potentially new technologies. The idea is you put in a lot of resources in order to develop something. You get to the point where you say, aha, here it is, and of course that's where you have spent the most amount of money, and the question is whether it's going to be successful or not is a big question mark, and it can sometimes be challenging to actually get to emerge from that valley. So the question of whether that will happen with millipede-based technologies is still an open question, and a lot of it depends on the competing technologies. So one of them, again, is flash. Flash is suffering from the same problems that silicon has, basically getting more and more difficult to scale it further down. And they're basically the dashed lines that you see here, these are all projections, basically the cost in dollars per gigabyte. And depending on how they go, it's not clear whether the flash will really find some competition from probe-based storage. Probe-based storage has still a lot of, it would still have a significant amount of development work, and it's not clear what the lifetime would be and how many cycles it would be able to provide superior performance. So what's the main message of this talk? The medium is the message of this talk. And this is really the second half of what I want to tell you. So we're going to go back to this diagram here, the semiconductor roadmap, and ask ourselves why it is that silicon has been so successful, or semiconductors in generally. So there are properties of semiconductors that make it extremely useful for information technology. And I would argue that there are three main properties that in fact are also shared by another material system that I'm going to be focusing on in the remainder of this talk, oxides. So the first property is that the conductivity of semiconductors can be varied over an enormous range. And this can be done either through doping, N or P-type doping, or through field effects. And of course both of these are used in real devices like transistors. So this is the fact that they are semiconductors is what makes them so useful, that you can basically turn them on and off permanently or temporarily. And this is something that is also shared by oxides. Oxides have the ability to work through this metal insulator transition, and that's something that can potentially be useful for devices. So a second property is that there's the ability to make insulating layers that can separate the conducting channels that are used and that are switched by gates. So the idea is you want to have a metal, an insulator, and then some channel, and the metal would be the gate. And this is something that is readily done with silicon. You can oxidize silicon, form SiO2, glass. But oxides themselves can be great insulators, and so this is something that even the same material can in fact serve both as a conductor and as an insulating barrier. The third property has been simply Moore's law, the ability to scale these devices down to nanoscale dimensions. And this has been taken, of course, 4 decades to get to the point where we are now. So maybe in time any material can be scaled down, but this is something that was certainly required in order for silicon-based devices to get as far as they have already. But what I want to tell you about is some properties of oxide materials that in fact may be far superior in terms of their scaling, and that in particular, along with the other two properties, make them very attractive candidates for information technology. So I'm going to be focusing on a material, strontium titanate, and this material has been known for many decades to exhibit a very wide variety of behavior. In fact, you could call strontium titanate the hydrogen atom of solid-state physics. And Marvin Cohen, a theorist who was the one who actually predicted the superconducting properties of strontium titanate many decades ago, he wrote this about strontium titanate. He said that the complexities of the crystal structure, lattice waves, band structure, transport properties, impurity electrons, and superconductivity have inspired the comment, which was their comment in fact. If strontium titanate had magnetic properties, a complete study of this material would require a thorough knowledge of all of solid-state physics. Now, in recent years, there have been, in fact, several reports of very interesting and not well understood magnetic properties of strontium titanate. So that does round out the properties. And so this is a very exciting material that I would say moves along the horizontal axis, this more than more axis, where these properties can be used potentially for future technologies to broaden the appeal of information technology. So the properties that of the strontium titanate are going to be influenced by a very thin layer of lanthanum aluminate. These are both by themselves nominally, when they're undoped, they're insulators. Lanthanum aluminate is also a wide band gap semiconductor. And when lanthanum aluminate is grown on TiO2 terminated strontium titanate, it can be modeled very simply as alternating positive and negative sheets of charge, the formal charge of these LaO and AlO2 layers. And that really means that there's a polarization which is pointing downward toward the interface. And that charge density can be represented here as a series of delta functions of alternating sign, positive and negative, which can be integrated to produce to represent the built-in electric field in this polar material. And then you can integrate that electric field to see a potential that is linearly diverging with the thickness of the lanthanum aluminate. So this potential can get very large, and it in fact can lead to an electronic reconstruction. And when that takes place, the polarization of the lanthanum aluminate is screened in part by electrons that are bound to this interface, and that's represented here. So then that polarization then can be, that discontinuity can be, can lead to the formation of a quasi-two-dimensional electron gas. And this was reported first in 2006 by Harold Huang's group. Sorry, it was first reported in 2004. This diagram is taken from 2006 paper. In 2006, there was another group led by Jochen Manhart at the University of Augsburg. They explored the insulator to metal transition as a function of the increasing thickness of the lanthanum aluminate layer. So what they found is that if there are 0 or 2 or 3 unit cells of lanthanum aluminate grown on strontium titanate, as I had indicated before, that the interface was insulating. And when they put 4 or more unit cells, then they found that there was basically a conducting interface. So there's a very sharp transition that took place between essentially 3 and 4 unit cells. So here the conductance is very low, here it's high. And what they also found, very surprisingly, was that you see these red circles here. These red circles indicate that in fact the 3 unit cell structure was bistable, in that it could be either conducting or insulating depending on the prior voltage applied from the back of the strontium titanate substrate. So in a subsequent experiment, they could begin with an insulating interface. Here we're plotting resistance now on a log scale, and by applying 100 volts to the back of the strontium titanate, they could then switch the interface to the conducting state, and when they turned off the voltage, it remained conducting. And they could switch it back to the insulating state by applying minus 100 volts. So in some sense, this was a bit, because it could be switched by this voltage, although a large voltage, and could the insulating or conducting state of that interface could be used to store information. So I was very intrigued when I learned about this, during a visit that I made to Augsburg over the summer of 2006. And it inspired me to try to see if it was possible to locally control this metal insulator transition. And if you can do it locally, then you have the potential of making many, many bits and having some impact for information technology. And the idea is basically very similar to the Etch-a-Sketch, which is a toy that I used to play with as a child, and I was never able to make anything remotely as beautiful as this drawing, which was clearly made by somebody who put it on the web. But basically this is the Etch-a-Sketch as it looks like from the outside, and if you were to open it up, you would find that there was basically an enclosure with fine aluminum powder, and this powder naturally sticks to the glass surface. And when it sticks, it basically forms a mirror, or sort of a diffuse mirror surface that looks bright. And this stylus here is actuated by these knobs, so it can be moved, and it scrapes off the aluminum powder as it moves either in the horizontal direction or in the vertical direction. And so that allows light to pass through, and it does not reflect, and it looks dark. What's also really wonderful about this toy is that it's a rewritable surface, that you can turn this upside down and shake it, and the aluminum powder will then return to the surface and it will look bright again. And so this is of course a perennial toy. But in the laboratory, of course, we don't have toys, we have tools. So we use atomic force microscopes, and instead of a blunt stylus like this, we use a very sharp AFM probe, which has been coated with metal and can allow us to apply voltages to the top surface of this oxide heterostructure. So the way that it works is as follows. The green areas indicate regions that are conducting, or the electrodes. And so we can monitor the conductance by putting a voltage, let's say, on one end and measuring the current on the other end. And in this region here, we have insulating area, and so there's no way for electrons to flow from one side to the other. What we can do then is take an AFM probe and apply a positive voltage to this and move it across the surface, and when it does, it locally switches the interface from the red insulating phase to the green conducting phase, creating a wire. And we can monitor the conductance, or the current, if we apply a small voltage, as we move this across, and we find that when we complete a circuit, we see that the current jumps up. Now, just like the Etch-a-Sketch, we can then take this structure, and instead of applying a positive voltage, we can apply a negative voltage and move across the wire. And the idea is that we may be able to undo the writing process that we've created. So when we do that, we can also monitor the conductance, and we find that it goes back down to this insulating state. So we are able to reverse it. But what was really surprising to us when we did these experiments was the sharpness with which it went from the conducting state to the insulating state. And in a sense, it provides a measure of the width of this wire. And the structure that we created here, using plus 3 volts and minus 3 volts, allowed us to create a wire that was only 2 nanometers wide. So by changing the tip voltage, we can make the width of the wire go from 12 nanometers with 10 volts down to 2.1 nanometers with 3 volts. And these are the widths for wires. As I was saying before, we can write and erase. In fact, we can do this multiple times. So in some sense, this is the analog of the experiment that was done in the Augsburg group, where they were able to switch repeatedly the interface between conducting and insulating. However, we're doing it over a very small area, and we can do it hundreds of times without any problems. So this is a rewritable interface at the nanoscale with feature sizes that are in each direction about 1 million times smaller than the Etch-a-Sketch. So the dot size is about 1 trillion times smaller than what you can achieve with an Etch-a-Sketch. So we have been doing some work since that initial publication, 2008 and 2009, where we are trying to understand the physical mechanism for why it is that the interface is able to switch back and forth between the insulating and conducting states. I don't want to say too much about it, but I want to give some physical picture here so that it becomes clear what we're doing is more akin to a type of surface modulation doping, where the presence of positive charge that is placed and removed by the AFM probe is able to gate locally the structure, creating these electronic straits and then removing them later on. So we believe that water plays a critical role in the writing process, and the water will naturally adsorb onto the lanthanum aluminate surface. But if a water molecule is adsorbed like this, it's still electrically neutral, so it's not actually charging the interface and is not expected to create electronic states at the interface. So it's not charging the top surface. However, we can remove this hydroxyl group here with the application of a positive voltage, leaving the hydrogen terminated surface here, and this H plus here is going to attract an electron to the interface. And then by changing the polarity of the voltage applied to the tip, we can then remove that hydrogen and then leave a clean bare surface where another water molecule is free to come down and grab onto the surface. So that would take us back and allow this cycle to continue. This is, of course, a very simplified model, but in fact, it's really, we do know from experiments that are published recently that if you do not have water, then you cannot write structures, but you can erase them under vacuum or under dry air conditions. And that's consistent with this simple picture. So the idea is that this material, this oxide interface, works very similar to in a manner similar to a field effect transistor. So this is a very simple picture of an enhancement mode field effect transistor, MOSFET, and here you have an insulating layer and a gate, and so the channel here is basically insulating, and so this would be the off state of the transistor. By putting positive charges on the gate, you can attract electrons to this interface and turn this switch on. The material that we're working with is very, very similar. You have a very thin layer here, 3-unit cells of an insulator, and in the absence of positive charges here, you might have 2 wires that are close together but still no conduction between them. And by writing on the top surface and depositing this positive charge, we're able to close this gap and switch the material to the on state. Now, but in some sense, this is like an ultra-dense array of transistors. So we can string all of these transistors together in complex 2-dimensional designs to create a very broad range of device technologies, potential technologies. So I want to go through and discuss some of the experiments that we've been doing, both at room temperature and a few things at low temperature. And well, one of the things that we tried to do was to determine the smallest size at which we could put quasi-zero-dimensional islands. And so we did an experiment where we looked at the insulator to metal transition, where instead of applying a continuous voltage, we used a voltage pulse that was on for some duration that ranged from microseconds to milliseconds. And we pulsed these islands and separated them by a distance d, and looked for a sharp transition where below some critical distance these dots were overlapping and led to a conduction between these 2 leads, and above which it was insulating. And so what we found basically is that we could then reach this point where at about 1 nanometer we were able to create the structures that are distinct on the scale approaching 1 nanometer. So we also thought it was important to try to develop a transistor, a field effect transistor, which we named even before we did the experiment. And the transistor that we developed is actually quite simple compared to the way in which transistors are now made. So this is an animation taken from the Intel website, and you can see that the process of making a single transistor is quite complicated. There are many steps involved. You have additive steps where you're, for example, doping the material. You have other places you want to etch materials away. And then there are other transformative steps where you're converting, for example, silicon to silicon dioxide. And all of these have to, of course, work, but you're doing things in parallel, so you take advantage of that and you make billions of transistors on a single wafer. The transistors that we're making are smaller, actually, than those the ones that are currently being used in silicon. And there are a few steps. So we begin with writing a T-junction. There are 3 leads here. We'll call these a source and a drain and gate. And we begin by writing a T-junction. And we're just going to write a line with 10 volts. So we create 12 nanometer wide wire. And then going to erase a 1 micron square area that will allow us to rewrite with a smaller wire that's about 2 nanometers wide. Now at any given point we can monitor the properties of this device, unlike that of silicon-based transistors. So in this case, if we have a T-junction, it's just a resistive network, and so we expect to have a linear IV characteristics that are shifted up and down by whatever voltage we apply to the gate. So this would be an extremely leaky transistor that's always on, for example. But all we need to do is make a slight modification where we form the channel and then move the gate a little bit back, and this is the essence of our sketch FET. So the transistor basically works by applying a positive voltage to the gate, which then allows electrons to move through this channel. And you see that when the gate is 4 volts, we have a straight line here between the drain current as a function of the voltage between source and drain. So it's limited by, the current is limited not by the impedance of the channel, but rather by the leads themselves. And when you lower the gate voltage, what happens is basically becomes more and more resistive, and then eventually it basically turns off altogether. And you can see actually that these curves don't all cross to 0, and that's because there is some leakage current here, which can be controlled by changing the distance here between the gate. So as a transistor, this device can actually work at frequencies in excess of gigahertz. So the initial reports, they maxed out at about 5-10 megahertz. But by making the leads less resistive, we were able to push up the frequencies well into the gigahertz regime. So this material is much more than Moore in that there are many properties that are going to be of interest. Recently we developed a photoconductive switch and have been using this in an ultra-fast mode to generate nanoscale or molecular scale terahertz pulses. This is a talk that was also given at the APS March meeting. As I mentioned before, we have demonstrated that these transistors, these sketch FETs, can operate in frequencies in excess of gigahertz. And we also have demonstrated that by changing the voltage profile along the wire, we're able to create rectifying regions that mimic the behavior of Schottky diodes. So the nanoscale photodetector was actually, that work was recently published. So the idea is you have, you create a wire and you cut it, and that junction it becomes sensitive to light, that you can close the switch here not using a third terminal gate, but rather using a focused light beam. And it turns out to be a very sensitive detector that's tunable with the very large electric fields that are applied between source and drain. And it's interesting for sort of molecular scale spectroscopy. Also, we have some work that is going to be published shortly. It was also discussed in a paper at the March meeting, where we created a single electron transistor, and it's incredibly simple to make these transistors. We simply write, in one instance, a cross, and then move to the center of the cross and apply an erase pulse, which creates a cylindrical barrier region, and then without moving the probe at all, we have a self-aligned positive voltage pulse that is applied that creates the island. So this gives us an island with a source and drain and two side gates. And it's interesting that this system, well, it actually works at relatively high temperatures and tens of Kelvin. It also is interesting that the strontium titanate in those temperature range is ferroelectric, so it looks like the barrier regions are behaving in a hysteretic fashion, allowing you to switch between the Coulomb blockade region and the resonant tunneling regime simply by altering the ferroelectric polarization in the barrier. So this is a very interesting system because it's basically at the smallest scales for so basically literally single electronics. It's a single electron transistor. It doesn't have to have only one electron in it, but this one does. We can have 0, 1, or 2 electrons in this very tiny area, and that's very interesting for scaling and for also perhaps making very sensitive mechanical detectors and electrical detectors that can be used for probe storage. And I will just mention that there is a variety of interesting phenomena at low temperatures. So these materials also become superconducting, and we can write structures that undergo this quantum phase transition to that allow the formation of Cooper pairs. And that's a very interesting regime that goes beyond the information technologies. That's the scope of this talk. So getting back to this idea of having a rewritable memory and including new functionality like logic is a very interesting prospect. So traditionally, memory and logic are made from different materials, although if you think about flash, then of course that's also silicon-based, but it's usually a distinct chip. And transistors, like even the successors of the Penryn, are still much larger than the features that we're able to create using this oxide heterostructure. And the same is true for flash. So the Millipede project is very interesting, even though it has essentially been shelved by companies like IBM and Hitachi and Seagate. But the idea that one could shrink not only the devices themselves, but what is required to create chips that are perhaps even fully functional, that scaling basically is really amazing. Being able to take the functionality of a fab, which creates, to scale the functionality of a fab that creates chips that are capable of doing complex processing of information, scaling them by basically 10 orders of magnitude from the size of the 17 football fields that make up Fab 32, Intel's fab in Chandler, Arizona, to something that's basically the size that can fit in your hand. So those of you who know about the Millipede project know this is not such a crazy idea of something fitting in a handheld device, but being able to create something much more than memory is interesting for future technologies and provides many opportunities. But of course, with opportunities, there are challenges, especially for oxide nanoelectronics. One thing is that for those of you who are expert in oxide nanoelectronics, you know that the strontium titanate substrates are notoriously unreliable. They're small, they're hard to work with. What you would like to have is some type of oxide wafer that is of comparable size to what you have for silicon. Well, we've actually have been working with both LSAT and silicon as a host carrier for growing strontium titanate. This is my collaborator Chengbom Ohm, and with them we have been working to try to see if indeed we can write nanostructures on the substrate. So the idea would be to have lanthanum aluminate on strontium titanate on either LSAT or silicon. And so it turns out that we're able to do that for both of these, and we have publications there are publications to describe both of these. Actually, our work of writing was presented at the March meeting, but was not in this publication. So the other question is whether there may be other probe-based approaches that have not come from the Millipede project. What about the megapede? Well, megapede would be something like 10 million or millions of probes. And I just want to highlight some of the beautiful work done by Chad Merkin's group over the last few years. And he took a different approach where the idea of to try to simplify the whole process. So instead of having feedback loops and optical levers for each of the individual probes, he decided to try to change the idea of how the probe interacts with the surface by including a soft elastomer cushion between the probe and the hard substrate. And so over the last few years they have shown that it's possible to make millions, maybe even as many as 11 million probes on a single wafer. And on these probes are tips that are very sharp, and this is the most recent paper where they've made extremely sharp, hard tips in very large arrays that are grown on, they're silicon-based, and very interesting for this further scaling up of all of this. They've also have shined light through apertures that were created in these, and it's a very exciting alternate approach towards the scaling of probes. This is just showing the process, which is incredibly simple. It's a lot simpler than the Millipede idea, and is something that can be made very inexpensively. And the way that they had proposed and actually planned to apply these probes is to attach the entire wafer to a piezo scanner, and to move it up and down, and then touch the surface and perform, for example, shine light through the probes, I think in this case. And in doing so, they could create millions of parallel devices. And it's possible, in fact, to using liquid crystal displays and so forth, micromirror displays, to individually address these devices. Okay, so let me summarize. The idea of having an AFM or 1,000 or 1,000,000 AFMs in your pocket is not a crazy idea. It is something that's the so-called quad-core, that's how I termed it, quad-core millipede has already been demonstrated. What you might have thought to be the most difficult and challenging part, the hardware associated with the AFM itself, has that problem has been solved, and there may be approaches that would scale up the number of probes even further. But maybe again the message is the medium with the new materials, perhaps the one that we have that I've just described. With the oxide electronics, we can basically have much more and much more than more, and perhaps reach densities in excess of 100 terabits per square inch. That's 2.5 nanometers square distance between bits, and I think that's something that we can do with our system if we can read it out properly. And perhaps integrate not only the memory capabilities, the on-off, but also logic and perhaps complicated sensing as well. So there's a great amount of promise, I would say. There are many challenges, and in the next few years perhaps we will see whether it is impossible or not to put an AFM in your pocket, and thousands of them, and have them do something useful. So to paraphrase the famous saying by Richard Feynman, there's plenty of room for probes at the bottom. Thank you for watching. So I'd like to acknowledge the group, my group at the University of Pittsburgh, especially Chang Sen, who did some of the pioneering experiments in the oxide nanoelectronics. as well as the colleagues Jochen Menhard, who introduced me to this material system, and Changbom Om, who has been a very active collaborator with me, as well as Yuri Suzuki, and theory interactions with Steve Helberg and his postdoc at the Naval Research Laboratory, and TEM from Shaoxing Pan at University of Michigan. And last but not least, this work is made possible by the support from various funding agencies, including the National Science Foundation, DARPA, the Army Research Office, the Air Force Office of Scientific Research, and the Fine Foundation. Thank you again.